was saying is if you score what I consider, safely, in other words, I don't have any suspicions of any cheating or anything like that, and you take a comprehensive final exam and score, say, a 95, 96, 97, something like that, then even if your grade doesn't work out to be an A, I'm probably going to give you the A anyways. I never put that in writing, so it's not quote unquote required, but that's what I do. Same thing with a B. If you end up getting like an 85 to 89 or something like that on the comprehensive final, and there's no doubt that you didn't cheat or anything like that, then I will give you a B even if the grade doesn't work out to that way.
O-
That being said, otherwise I'm just getting your grade. So like if you get like a 92, uh, that's not the top half of an A. But if the grade works out to be, for instance, F, I'm probably still going to give you a B for that.
Okay, thank you.
Does that make sense?
Yeah.
Yeah, it's just really at the end of the day, the final exam is the time where you really have to peak. So I make my exams comprehensive. I don't let people skip them. And for that reason, that basically that's part of the reason why I do all this is so that the student can have one last chance to make up for all the screw ups and hopefully get, a little bit of positive out of their out of their life after finishing a physics class so hard. So,
Okay. All right.
all right.
Thank you.
No problem. I got you guys. I'll watch out for you. I care about you, and I want you to do the best you can. So I'm always uh, doing two or three different calculations for grades to see what the best grade I can get you is based on your own performance. I'm not trying to give away points. I'm just trying to make sure all of you guys do as well as you possibly can. So feel free to ask me questions about that anytime. I think we're gonna go ahead and get started. I started up the section on center of mass last night, and I quickly realized that I didn't have enough time. So I'm going to do a couple of simple, uh, discrete calculations of center of mass from your book, and then I'm going to do a couple of the ones that require integration. And I'm still asking you guys to keep an eye out for your email because I might, over this weekend, I might send out a video that I want you to have watched before you attend class on Tuesday. So just do that for me. That would be helpful. I'm going to try to play catch up a little bit. I might even cover a good fraction of chapter 10, if not all of chapter 10, via a video like that. And then when you come into class, I'll solve a couple problems and give you a chance to answer questions or ask me questions, and then I'll go on into the next chapter. So that's what I'm trying to do. Make sure I got to get you guys through 14 and 15. And normally the way it goes is after 9, I cover 10 and 11, and then jump to 14 and 15. One more thing I got to announce to everybody. So please, 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 everybody, listen to this. I have two or three students that have, in a couple cases, more than one online test that's been missed. And I look, and I've actually, for all of those students, I've actually opened the test back up again to give them yet another chance to do it. Well, I've done that again. So if you, and this is on you, I'm not taking the time to tell you, hey, you missed an online test. This is something you should know that you missed. So you need to check your grade book, find if you missed any online tests. If you did, you've got till the Sunday to do them, or the zero will stay. So make sure you get that. I did open up that, and I opened up the practice test for all the people that missed. If you missed online test one, I opened the corresponding practice test, and I opened online test one, both of which have to be done by 11:59 p.m. on Sunday the 5th. So make sure you guys get that done. Hopefully everybody will hear this, and I'll be posting this tonight. I think that's about it. So let's go ahead and get started. Anybody have any questions before I share my screen and get started? It does
All
not
right.
appear. Go ahead. I
Sorry,
hear.
I have one. I'm always so delayed.
No problem.
With the remainder of the course, how many more face-to-face tests do we have? And then, like, I know the final also is like a in person.
Yeah, you have one more face to face, and then you have the final that you have to schedule at a testing center or with your lab instructor and stuff like that.
Okay. All right, cool. Thank you.
No problem. And I haven't guaranteed that I'll drop the lowest of the three face-to-face tests, but that's my intent, and I hope to be able to do that. But if I get a lot of students choosing not to take test three, then we're not going to drop any of them. So just keep that in mind. All right. So I wanted to start off using the center of mass calculations. I also want to refer you to the module for this week. You'll see. I'm trying to remember what I called it. Let me look up there really quickly. I'm going to look in the module section of our Canvas course, and then I'm going to go down to the module, which I believe is week 11. Let me double check. Okay, that's way up in face-to-face test, so that's not anywhere near it. Oh, I have it in week 10 anyways. So there is a video in week 10 that says cannon fired in big rolling box solved using conservation of momentum. And then there's another one that says cannon fired in big rolling box solved using center of mass. Those two examples are really good examples that show you how you can get the exact same results we do from conservation of momentum by using the idea that when the net force acting on the system is zero, the center of mass can't move. So just like when the net force is zero, momentum is conserved. When the net force acting on a system is zero, the center of mass doesn't move either, and that's one of the ways I can show you. You'll also notice there's a calculating center of mass of a framing square. That's a neat problem. It's a little bit more awesome than the one that the book's given you, but either way, it's a good problem. So all of these problems in there are really good to look at. If it says LEC, like it says LEC 10, 25, 23 in parentheses, that means it's a full lecture. So you're not required to watch the full lecture, but you should watch the examples. If it doesn't have that in it, then it's probably just a particular problem. But even then, the problems usually take 15, 20 minutes when I'm doing them and explaining them. So make sure you check that stuff out to help you. It's going to be extremely important in chapters 10 and 11 because we've got to fly through those so quickly, and 14 and 15 for that matter. So let me start off by working. I'm going to skip example 914. That one's really, really, really trivial. So I'm going to skip that one and go to example 915. It says three particles in two dimensions. Three particles, each of mass 2.50 kilograms, are located at the corners of a right triangle whose sides are 2.00 meters and 1.50 meters long, as shown in figure 925. Locate the center of mass. So with this one, you can sort of pretend it's like maybe it's a triangular piece of plexiglass that's thick enough to hold these masses, but it's so light that it doesn't compare to the 2.50 kilograms. So you could imagine them being fixed to that piece of plexiglass that's the same shape of the as the triangle. And then you're trying to find out where on that plexiglass can I put my finger so that I could balance this. So, it might be some, let's say, New Wave restaurant that has a has a triangular tray for you to carry the drinks and stuff out. So, anyways, that's example 915. Let's look at it. So, example 915, and the important part of this really is more the diagram. We know we're looking for the center of mass. I know that X is this way, Y is this way. Each of the masses is 2.50 kilograms. So this is MA equals 2.50 kilograms. And then if you go a distance of 2.00 meters, you'll run into another mass, and this one's M sub B, and M sub B is 2.50 kilograms as well. And then if you go up a distance of 1.5 meters, then you have yet another mass, and that mass is M sub C, and M sub C is 2.50 kilograms, like that. Uh, what we want to locate is the center of mass, and what we know is the Y center of mass is equal to the summation from I equals 1 to N of M sub I y sub I. I don't know why I started with y this time, but I did. The summation from I equals 1 to n of m sub I. And similarly, the x center of mass is the summation of m sub I x sub I over the summation of m sub I. So let's start off with xcm. So xcm is going to equal 2.50. Now you might notice that each of these have the same mass. So I'm going to pull that mass out in front, and then instead of having mx plus mx plus mx, I'm going to have m parentheses x plus x plus x. So the x coordinate of mass A is 0, so I'm going to put 0 there. The x coordinate of mass B is 2.00 meters. And the x coordinate of mass C is also 2.00 meters. So that's the numerator. The denominator is 3 times 2.50 kilograms. So I'll just write it that way. And now we can see that the 2.50 kilograms is going to cancel out with the 2.50 kilograms in the top. And I'm just going to get 2 plus 2, which is 4. And then 4 divided by 3 is 1.33333 because 3 goes into 4 one time and it has 1 left over, and 1 over 3 is 0.33. So XCM is actually equal to 1.33 meters is XCM. Everybody follow that? Didn't miss anything? All right, now we're going to do the Y center of mass. The same thing works here. I got the same 2.50, so I'm just doing this because it can save me a little bit of time in writing. The Y coordinate of MA is 0. The y coordinate of MB is also 0, but the y coordinate of MC is 1.50 meters. And then I'm going to divide all this by 2.5 plus 2.5 plus 2.5, which I'm going to call that 3 times 2.5. So 2.50 kilograms again. And again, we can see the 2.5 kilograms is canceled out with the 2.5 kilograms. And this time, we have 1.50 divided by 3, which is just 0.500 meters, is equal to the Y center of mass. Any questions on that? And that agrees with the same answer they got. Now, notice in this case, if it wasn't for me arguing that we could imagine a plexiglass triangle or something like that on there, you really have no way of holding this quote unquote object up because there's 3 distinctly separate objects, right? So, in order for you to view it as something that the center of mass can be used for, you have to sort of put it on a platform of some sort. And the platform itself introduces another mass, and that mass has a center of mass, and you had to take into account that too. So if you were to actually embed that in a triangle, let's see what would happen. So I'm going to add to this problem and say example 915 extra. So let's imagine that uh, if the objects were secured to a plexiglass we don't know what happened there. Plexiglass triangular plate of mass let's actually say a mass 3.0 kilograms with dimensions, whoa, of 2.00 meters and 1.50 meters, where would the center of mass be? So this time I'm taking this and imagining, in addition to that, that there is a plexiglass triangular plate in there, and the plate has a mass equal to 3.00 kilograms. Now, I mentioned to you guys that the rule when you go to calculate the center of mass for a uniformly distributed mass, a smooth, homogeneous lamina. That's what they call it in the physics. I mean, in the math world, like in Calc 2 or something like that. It's basically a thin plate and it's homogeneous, which means that every square or cubic millimeter is exactly like every other cubic millimeter, so that the uh, geometric center will actually be the center of mass. And the center of mass of a triangle is 1/3 of the way from the vertex to the thick end, no matter which side you're going from. So, for instance, I have a vertex at the origin. If I move to the right, the triangle is getting thicker and thicker and thicker. In other words, wider and wider and wider, not really thicker, right? So, the rule is 2/3 of the way towards the fatter side will be the center of mass. So, the center of mass for the plexiglass uh, triangle should be at 2/3 of 2 meters. That's the X center of mass. The Y center of mass is if you start at that vertex at the top and move down, you go 2/3 of the way to the wide part, and that's where the center of mass is going to be there. So I can now say that the center of mass of my triangular plate, which is 1.50 meters by 2.00 meters, has a center of mass roughly here and here. So this distance from here to here is 2/3 of 2.00 meters. And this distance is 2/3 of 1.50 meters down that way. Okay. So now when I calculate the center of mass, I get this. X center of mass is equal to 2.50. Now, remember this is mass A, so that's 2.50 kilograms times 0 plus 2.50 kilograms. This one's at the 2 meter mark, so I'll write 2.00. And then the other one's also at the 2.00 mark, so I'll say plus 2.50 times 2.00. And now I've handled all three of them, but I also have to handle the actual triangular plate. And in this case, it's 3.00. And then 2/3 of 2 meters is 4/3, and 4/3 is 1.333, like that. And we divide all this by the total mass, which 3 times 2.5 would be 0.75, but then I add zero point 0.3 to it, so that'd be 1.0 or 1.50. So this is 1 point, no, not 1 point. So this is, sorry about that. This is 2.5 times 3 plus 3 gives me 10.5. Oops. 10.5 kilograms. So what I've got is 2.5 times 2 plus 2.5 times 2 plus 3 times 1.333. That gives me 13.99. and that's kilogram meters divided by 10.5 kilograms. And that gives me 1.33 meters is equal to the x center of mass. So notice we got exactly the same answer in this case, but I sort of expected that because I knew we had gotten 2/3 of the way when we came up with 1.333 for the x center of mass. So that one worked out. Let's see how the y center of mass will be changed. Notice that is roughly 1/3 of the way up, zero point 0.5 would be. So we'd also find that that might be fairly similar. In this case, now all we have to do is YCM is equal to 2.50 times 0 plus 2.50 times 0 plus 2.50 times 1.50. Now I'm going to say plus 3.00 times, in this case, it's only 2/3 of the way from the top. That means it's 1/3 of the way from the bottom, and 1/3 of 1.5 is zero point 0.5. So sure enough, we're going to hit it in exactly the same spot again. And then all of this will be divided by 10.5 kilograms. So in this case, I've got 2.5 times 1.5 plus 3 times zero point 0.5. That gives me 5.25 kilogram meters over 10.5 kilograms. That gives me 0.50 meters is y center of mass. So you can see in this case, even when I tried to take into account the plexiglass thing that I said we can sort of assume its mass is small and then it would be no effect. Well, by choosing it as a triangle of the same size and even using it as a mass that was a significant fraction of the other masses, I got exactly the same center of mass. But the important thing is you can see now how we can use objects if they have a geometric shape, they're not point particles like these dots were, then you just use their geometric center if they're uniformly distributed. If they're not if the mass isn't uniformly distributed throughout, the geometric center is not necessarily going to be the center of mass. In that case, you have to use a calculation like the integrals that I was showing you last time. Anybody have any questions on that? All right, your book does an easier one than the one that I was going to do yesterday, which was a triangle. I think I'll go ahead and do that first. It's the center of mass of a thin rod. And this is example 916. It says center of mass of a thin rod. Show that the center of mass of a uniform thin rod of length L and mass M as is at its center. B, determine the center of mass of the rod, assuming its linear density, lambda, its mass per unit length, varies linearly from lambda equals L0 at the left end to double that value at lambda equals 2L lambda 0 at the right end. So that's what we're going to do. And that is an important part that I wanted to point out to you guys. What I showed you last time was that the x center of mass is equal to the integral of x dm over the integral of dm. And there was a similar expression for y, but the important thing that you got to know is when you're doing this, you need to know what dm is. And dm can be gotten by, remember, density equals mass over volume. So, for instance, I told you that some high school teachers drew a heart like this. Well, that heart is what they use for density because they draw a line through it and then they realize its mass over volume is density. That's the kind of quantity we're dealing with here. But sometimes you're dealing with a quantity that's not fully three dimensions, like a spaghetti noodle, for instance. If you take a spaghetti noodle before it's cooked, it's long and thin. right? So it has no physical width this way, it has no physical height that way, but it's got a physical length this way. That's a good instance where we would maybe consider it to be a one-dimensional object, in which case lambda dm is equal to lambda, the mass per unit length, times dl, where dl is a differential length element parallel to the noodle, right? So if you laid the noodle along the x-axis, dl would be dx. If you laid it along the y-axis, dl would be dy, that sort of thing. Or if the object is two-dimensional, then you could use dm is equal to sigma dA. That's like a homogeneous lambda, like I was talking about with that little plexiglass rectangle. Uh, Another thing, a good example of a two-dimensional object is those big interstate exit signs. You know, those interstate exit signs you see hanging over interstates. They're a flat piece of metal that's maybe a 16th of an inch thick, but they're 4 or 5 meters wide by 4 or 5 meters tall. That really looks like a macroscopic width, a macroscopic height, but then the thickness is infinitesimal compared. So it really looks like in this case, it literally would be a homogeneous lamina because the paint weighs almost nothing, especially compared to the aluminum that they make the sign out of. And the aluminum is just aluminum, so the odds of you grabbing a cubic, nanometer of that sign and it weighing different than another cubic nanometer of that sign is slim to nil. So that's a homogeneous lamina. And in that case, you'd use sigma times dA, where sigma is the area density. It's measured in kilograms per square meter. Or finally, the old density that we're used to, and that is dm is equal to rho dV. So the dA is a differential area element and the dV is a differential volume element. Now, I'm going to use that to work this example 916. So example 916, and what we're going to do is we're going to embed it in an XY coordinate system. I'm going to say that the object is really thin in the Y direction and it's also really thin in the Z direction. Actually, let me do this a little better. So the Z direction, as I just mentioned, would actually be out of the board. That would be the positive Z direction. And what I'm saying is the thickness of this rod in that direction is very small. The thickness of the rod in the Y direction is very small. I've actually drawn it quite a bit thicker than I intended to, but the macroscopic length L is a macroscopic quantity. So that is actually a candidate for a one-dimensional object. Okay. If we say the total mass is equal to m, then that would mean lambda would equal m over L. That's if it's uniform. So that's another thing. When we tell you the mass is uniformly distributed, we mean the lambda or the sigma or the rho, the lambda, the sigma, or the rho are constants. That's what it means to be having a uniform mass. And this part A, calculate the center of mass if mass is uniformly distributed. Okay, so in part A, lambda is the density that we're going to work with. So we're going to say dm is equal to lambda dx, and lambda is going to equal m over L. In part B, however, lambda of 0 is equal to lambda 0, but lambda of L is equal to 2 lambda 0. And we want to calculate the center of mass then too. So that's what we're trying to solve here. Now, what I'm going to do is I'm going to draw a little differential mass element right here. That's dm is equal to lambda dx. The reason being is the width here is just plain dx. Okay? So now I can calculate for part A, x center of mass is equal to the integral of x dm over the integral of dm. So let's calculate the integral of x dm is equal to the integral of x times lambda times dx, and I'm going to integrate from x equals 0 to L, and it's uniformly distributed. So, and not only that, since it's uniformly distributed, I already know what lambda is. It's m over L, and 2, I know it's a constant, so I can pull that constant out in front, and it'll be the integral from 0 to L of x dx. So notice I replaced the dm with lambda dx, and I pulled the lambda out in front. The integral of x dx is 1/2 x squared. So this is going to be lambda L squared over 2 is the integral of x dm. Anybody have any problems with that? Anybody have any questions? Now I can go ahead and calculate the integral of dm. Notice it looks exactly the same. The only difference is I'm removing that x in there. So I'm taking the integral from 0 to L of lambda dx, which equals just lambda x. And x is evaluated at L and 0, so that's just XL. So now I can say that the x center of mass is lambda L squared over 2 divided by lambda L. You can see that I didn't even need the lambda, and I've canceled out all the L's, and I got exactly what we were asked to show, specifically the center of mass of a uniform rod is at its geometric center, so x center of mass is equal to L over 2. Any questions there? Okay. For part B, I'm going to try to make a linear relationship for lambda. So lambda of x is equal to mx plus b. And what we know is lambda of 0 is equal to lambda 0. And we know that lambda of L is equal to 2 lambda 0. So it's going to go from a uniform density lambda 0 to twice as heavy by the other end. So it's almost like having a meter stick or instead of a spaghetti noodle, imagine a spaghetti noodle that started off as one thickness, but by the time it got to the end, it was maybe twice as thick or, big around as a quarter. That's more or less what we're treating, only we're not doing it by showing geometrically the size getting bigger. We're just recognizing that the density is getting bigger. So using these two quantities, I can figure out a value. So lambda of 0 equals lambda 0 tells me lambda 0 is equal to m times 0 plus b. That means b is equal to lambda 0. And now if I use the other one, lambda of L is equal to 2 lambda 0. That one gives me 2 lambda 0 is equal to m times L plus b, and we just found out b was lambda 0. So now I can figure out that m must be, if I subtract lambda 0 from both sides, I get lambda 0 equals ml. So m is going to have to be equal to lambda 0 over L, like that. So I can now say that lambda of x is actually equal to lambda 0 over L times x plus lambda 0, which is easier to write as lambda 0 plus or times uh, 1 over L times x plus 1. So that's my density, linear density formula. And now I'm going to calculate the center of mass. XCM is equal to the integral of xdm over the integral of dm. So let's start off with the integral of xdm. That's equal to the integral of x times lambda dx. So lambda in this case is going to be lambda 0 times 1 over L times x plus 1 times dx. So this quantity right here is sigma, or excuse me, is lambda, and this quantity is dl. That's what we're showing here, and we're obviously integrating from x equals 0 to L. We can see that the lambda 0 is going to come out in front, and I get the integral of 1 over L x squared plus x dx from 0 to L. Obviously, 1 over L x squared, when I integrate that, that becomes 1 over 3L x cubed. So I've got lambda 0 times 1 over 3L L cubed plus the integral of x dx is 1 half x squared. So this is going to be 1 half L squared like that. So you can see that I get lambda 0 and then there's a common L squared, only this time I'm adding 1/3 plus 1 half, and 1/3 is 2/6 plus 1 half is 3/6. So 2/6 plus 3/6 is 5/6. So I get 5/6 lambda 0 L squared for the top. Now I've got to do the integral of dm, which again is the same thing. I'll pull out the lambda 0 and I'm integrating from 0 to L of 1 over L x plus 1 dx. That's going to be lambda 0 times, in this case, the integral of x is going to be 1 half x squared. So it's going to be uh, L squared over 2L. And the integral of dx is just going to be x, and that's evaluated from L to 0, so that's just going to be L here. So you can see that this 2 cancels out with that, so I get lambda 0 times an L times 1 half plus 1, which is 3 halves lambda 0 L. So my XCM is got to be 5/6 lambda 0 L squared over 3 halves lambda 0 L. You can see that the lambda 0 is disappearing, the L is disappearing in one case, and now I've got 2 times 5 is 10 over 3 times 6 is 18, so that's 10/18. And obviously 10/18 can be reduced to 5/9. So I'm going to say this is 5/9, and I don't know why I'm still writing in red. I was trying to write in blue. Uh, I'm going to say this is 5/9 L. So a little bigger than the middle, but that's the center of mass. Anybody have any questions on that? And that does agree with the result your book got. So any questions? All right. There's another one where they do Let me see it, 611. Yeah, there's another one, example 917, that's pretty good. So I want to explain that because it's not unlike the framing square one that I did. So I'm going to say example, and this is 917. In this case, determine the center of mass of the object below. So this looks like a framing square to me. That's part of the reason that I thought it would be good to cover. My framing square, I basically just took the whole weight of it and measured sort of the same thing this one did. Measured the thickness of the parts and the lengths of the parts and that sort of thing. This one can be solved without using calculus, and it can be solved still not necessarily a trivial way, but somewhat easier. So let me draw the shape, and I'm going to use the coordinate system that your book chose to use. So there's my x-axis, and this is my y-axis. And what we have is the corner of the square is actually at the origin. So I'm going to say this goes like this to right about there, and then this goes down. And this dimension should be a little smaller than that dimension, but not a whole lot smaller. And that was 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to say 1, 2, 3, 4, 5, 6, something like that. And this, and this. So the dimensions that we're looking at here are, this dimension is 0.20 meters. This dimension is 1.48 meters. This dimension is 0.20 meters. And then this dimension is 2.00 meters. And that goes all the way to there. Okay? So they don't give us anything about the mass. They don't tell us the total mass or anything like that, but they did say it's uniform, thin shape. So this is a uniform thin L shape. The uniform means that basically if I took off a square centimeter of it, that square centimeter would probably be a millimeter thick, and it would weigh a certain amount. Now, if I grabbed another square centimeter from another part of the square and weighed it, it would weigh the exact same thing. So again, we're using the idea that the density in some sense is a constant. This is because it's really, really thin. Remember, it's a more or less, this is like a framing square, which is used in construction. And normally that's about an eighth to a 16th of an inch thick. And then it's, on the order, not necessarily 2 meters like this one. It's usually on the order of, 2.5 feet by 1.5 feet or something like that. But the main thing is the fact that we know the dimensions and we know it's uniform tells us that the area, the actual area that we see, is directly proportional to the mass. So, for instance, if we consider this as two rectangles, we consider it as a rectangle that's 2.00 meters wide by 0.20 meters tall. Then if we took the 2.00 meters times the 0.20 meters, that would give us an area. If I did that for the other rectangle, that one would be 1.48 meters tall and 0.20 meters wide. If I took that area plus the other area, that would be the whole area. And what I'm trying to tell you is that the mass of part divided by the mass of the whole is a constant fraction. And in fact, I could say it's equal to the area of the part divided by the area of the whole. And that's just basically from the fact that uh, we can use sigma because it's essentially a two-dimensional object. So we could say sigma is mass per unit area. So we would say mass total over area total is equal to mass of the part over the area of the part. And from that, we can see that the mass of the part is equal to the area of the part divided by the mass of the total, or excuse me, by the area of the total times the mass of the total. So that's what we're going to use here. We're going to use an area as the stand-in for the mass because that unit's going to cancel out. And really, if we wanted the mass, we would say mass is equal to density times volume, or we could, if we wanted to take into account the thickness of the square. If we didn't want to take into account the thickness of the square, we could say mass is equal to sigma times area, and that would work as well. That's what we're doing here. So the center of mass for the x direction, the x center of mass, is equal to the summation m sub I x sub I over the summation m sub I. But we're going to let that be a stand-in because it's going to be a sub I x sub I sum divided by the summation of a sub I. So with that in mind, we're going to look at it this way. The area of the top rectangle is 2.00 meters times 0.20 meters. Now, technically, if you wanted to just see how the math worked out, then what we could do is we could work it back in terms of everyday things. In other words, use the actual density, the row density, and we would take this and multiply it by the thickness and then times the density. So that would give us the mass in kilograms because the green row is kilograms per cubic meter and the T is another meter. So I've got that, and now I've got to take the center of that. The x position of that horizontal rectangle is 1.00 meters. So I'm going to write next to it 1.00 meters because that's the x coordinate of that center. And now I've got to take the other part, which is 1.48 meters times 0.20 meters. Again, I'm multiplying this times the thickness times the density of the material it's made out of. And now I'm going to multiply this by the center of that. Now, remember, the center of it is 0.1 meter from the right side in, and the right side in is at 2 meters. So I'm going to subtract 10 centimeters from that. That's going to be times, oops, that's going to be times 1.90 meters. Someone just came in. And then all of that is going to be 2.00 meters times 0.20 meters times T times rho plus 1.48 meters times 0.20 meters times T times rho. So now you can see that this T times rho is just going to cancel out anyway. So that's again proving that we can just use the area as a stand-in for the mass. Now all I get is 2 times zero point 0.2 times 1 is equal to 0.4 meters. Oh, those were supposed to be, that was supposed to be a, yeah, that was supposed to be meter. That's cool. So that's meters cubed. And then 1.48 times zero point 0.2 times 1.9, that gives me plus 0.5624 meters cubed. All this is divided by 2.00 times zero point 0.2 plus 1.48 times zero point 0.2. This is 0.696 meters squared. So if I take zero point 0.4 and add to it 0.5624, that gives me 0.9624 cubic meters over 0.696 square meters. And that gives me 1.38 meters is the X center of mass. That's how we got the X one. Now we're going to do the Y one. And we'll do it the exact same way. Y center of mass is going to be 2.00 meters times 0.20 meters times t times rho. This time I'm going to multiply it by the y coordinate. Now the y coordinate is 0.10 meters up, so that's zero point 0.1 there, plus 1.48 meters times 0.20 meters times thickness times the density rho. And this time, the center of mass is going to be half of 1.48 meters down. That's zero point 0.5, zero point 0.7, zero point 0.74. So that's 0.74 meters downward. And again, I'm going to divide this by 0.696 square meters. So 2 times zero point 0.2 times zero point 0.1 plus 1.48 times zero point 0.2 times zero point 0.74 gives me 0.25904 meters cubed divided by 0.696 meters squared. And that gives me 0.372 meters is the Y center of mass. Anybody have any questions on that one? Now, I was rough estimating the sig figs. I didn't really pay close enough attention to discern exactly what they are, so I sort of did the trick that most authors do when they're writing solutions manuals, whereas even if you're adding stuff and you add nothing but 2 sig figs, you're going to assume the final answer comes out in 2 sig figs. That's not necessarily true, but that's the way it came out. I got 1.38, they got 1.42, and whoa, no, I don't know why they got what they got. Theirs differs from mine by quite a bit. Let's see. Oh, maybe I changed my numbers a little bit. Oh, yeah, I did. I called mine 2.00 meters and theirs was 2.06 meters. I guess it's because I'm old and missed some stuff. So yeah, it should be a little bit off and that's fine. Oh, and this should have came out negative, shouldn't it? It would have been negative 0.74. Ooh, that's the problem. The 0.74, let me fix that real quick. this right here was supposed to be negative 0.74, so all of this isn't correct. The other parts are fine except the fact that I used 2.00 instead of 2.6. So I'm going to fix this real quick and fix this real quick. Hopefully this will do it. So now this is negative 0.74 meters over that way. So that's going to make a marked difference. So in this case, I'm saying 2 times zero point 0.2 times zero point 0.1 minus instead of plus 1.48 times zero point 0.2 times 0.74. I put the minus in there, so that's why I didn't have to type minus 0.74. And this gives me negative 0.17904 cubic meters. And now I divide that by 0.696 square meters, and that gives me a really, 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 really small number. Oops, never mind. Evidently, my fat finger missed the decimal point, so I divided it by 696 instead of by 0.696. So that should give me negative 0.257 meters is equal to the y center of mass. Now, anybody have any questions on that one? All right. Now I'm going to go back to the one I started with earlier last time where I was working the center of mass out for a triangle. So let me just do it this way. Consider a thin triangular plate of mass m, height h, and width w if the mass is uniformly distributed, then find the center of mass. Okay, so I'm going to draw my coordinate system again. There's my x-axis, there's my y-axis. I'm going to say that the object is a triangular plate like this. This dimension is W, and this dimension is 8, H, excuse me. And this is the triangular plate we're talking about, and its total mass is M. Now, can anybody tell me which dm we're going to use? Are we going to use dm equals lambda dl, or dm equals sigma dA, or dm equals rho dv? Which one of those? Let me see if anybody typed anything in the chat. They have not. So y'all don't know which one of those DMs we're going to use? Is it two-dimensional, one-dimensional, or three-dimensional? Yeah, it's two-dimensional in this case. Everything's three-dimensional to be honest with you, but when the dimension of thickness is so small compared to the other two dimensions, we can consider it two-dimensional. So what we're going to use is dm is equal to sigma dA. The fact that it's uniformly distributed tells us that sigma is in fact a constant, and though we don't need it, this is what sigma would be. Sigma would be m times 2 over h times w. And the reason the 2 is up there is because it's m over the area, and the area is 1/2 base times height. 1/2 in the denominator is the same thing as a 2 in the numerator, so that's why it would be that. We just don't need it, but either way. I wanted to show it to you so you'd know, have some idea what this is. Notice the units of lambda would be like kilograms per meter, whereas the units of sigma would be kilograms per square meter, and the units of rho would be kilograms per cubic meter. That's the key thing to help you understand this. Now, the x center of mass is equal to the integral of x dm over the integral of dm. And what I was trying to explain to you last time is you're integrating x over dm. So this differential mass element and has to have an x value that doesn't vary macroscopically from one side of dm to the other. In other words, if I used, a differential mass element like that, you can see that the x differs on the left side from the right side by a macroscopic amount. So that's not a good thing. So instead of doing that, we try to choose a differential area element that at least in x is only infinitesimally different from x on one side to x on the other side. So I'm going to say let dm equals sigma dA, and for dA, I'm going to take a little rectangle like this. The width of this rectangle is dx. The height of this rectangle is y, and it's actually y minus 0, where y is the function that represents that diagonal line. Now, I think you can figure out how I know this, but y is equal to h over w times x. That's what that y function is. And the bottom of the triangle is the line y equals 0. So that's why I said it's y minus 0. And that gives us h over w. I really drew that badly. H over w times x is the height. So now I can go ahead and integrate it. So the integral of x dm is equal to the integral from 0 to w of x times sigma times dA. And the sigma is a constant, so I'm going to pull that out in front. Integral from 0 to w of x. Now the dA is going to be h over wx times dx. What I'm pointing out here is this is the height, and this is the width of that rectangle. So this whole thing is the dA that we're talking about. Everybody follow that? So now I have sigma h over w times the integral of x squared dx from 0 to w. That's going to give me sigma h over w times 1/3 W cubed. So this is equal to sigma h W squared over 3. Now I got to do the bottom, which is the integral of dm, which equals the integral of sigma dA, which equals sigma times the integral of dA, and the integral of dA is just the integral of h over w x dx, integrating from 0 to w. So this one becomes sigma h over w. The integral of x is 1/2 x squared, and this is evaluated at w, so this will be 1/2 w squared. Therefore, we're going to get sigma h w over 2. So the x center of mass is equal to the integral x dm over the integral dm. So the x dm is sigma h w squared over 3, and the integral dm is sigma h w over 2, and you see that that becomes 2/3. You see that the sigma cancels out with the sigma, the h cancels out with the h, and the w squared cancels out with the single w downstairs. So I get 2/3 of w, which is exactly what we predicted last time as well as earlier when we did a triangle. Anybody have any questions on that? So the other one's a little bit more complicated. To actually work out the y center of mass, I'm going to draw a different diagram just so it makes it hopefully a little clearer what we're doing. And I don't know why I drew that red, but here we are. So again, I'm going to say this is H, this is W, like that. Now, this time I want to calculate the y center of mass, and remember the y center of mass is equal to the integral of y dm over the integral of dm. This time I have to consider a dm that doesn't change much in terms of y from one edge to the other, so I need the size of dm to have a minimum y and a maximum y, and they can't differ more than by an infinitesimal amount. So with that in mind, what I'm going to choose for my differential mass element will be this quantity right here. Now, you might actually picture it as this whole rectangle here, because this right here is a height dy, and this equation for the diagonal line, we already know it's y equals h over w times x, but we're going to interpret it as h or x equals w over h times y, like that. So what I'm going to say is the height of this rectangle, or the width in this case, is equal to w minus x, where that's my x value right there. So I'm going to use that x as a function of y to figure out what that is. And like I said, the dy is straightforward. Now we're going to go ahead and say the integral of y dm is equal to the integral of y sigma dA, which equals sigma times the integral of y. Now dA is going to be w minus w over h times y. That's the height. and or that's the width, I should say, and the height is dy, and I'm going to integrate from y equals 0 to h. You can see I've got a common factor of w there, so I'm going to go ahead and pull that out too. I got sigma w times the integral from 0 to h of y minus y squared over h dy. So that's sigma w. The integral of y is 1/2 y squared, so this is going to be 1/2 h squared minus, now the other one's going to be the integral of y squared. That's going to be 1/3 y cubed. So this is going to be h cubed over 3h, like that. And you can see that this h in the bottom is going to cancel out with the 3 up top and make it a h squared, so that now I can have a sigma, a w, and an h squared that's all out in front. And then we just got 1/2 minus 1/3, like that. And 1/2 is 3/6, and 1/3 is 2/6. So 3/6 minus 2/6 is 1/6. So we're going to have sigma w 8 squared over 6 for the numerator integral. The denominator integral, integral of dm, is just equal to sigma times the integral from 0 to h of w times 1 minus 1 over h times y dy. That's going to be sigma times w integral from 0 to h of 1 minus 1 over h y dy. So that's going to give me a sigma w out in front. And the integral of dy is just y, so that gives me an h. The integral of 1 over hy is y squared over 2h, so that's going to be h squared over 2h, like that. And now we can see that this is going to be sigma wh, because there's a common factor of h in there, times 1 minus 1/2. So this is 1/2 sigma wh. So YCM is equal to the numerator, which we got was sigma HW, or excuse me, sigma H squared W over 6 divided by sigma WH over 2. So that 2 is going to come to the top, and that 6 is going to be in the bottom. So that's going to make a 1/3. And then everything else is canceling out except for the h. So the y center of mass, as predicted, is 1/3 h. Any questions? All right, everyone. I think that's enough. We've done more or less all the examples from the chapter. Uh, That's plenty of center of mass examples. That's plenty of conservation of momentum examples. I'm going to go ahead and tell you guys you're free to go. I will remind you that if you have a outstanding online test, that's up to you to figure out. And if you do, you've got to get it done by Sunday or you're going to get a 0 on it, and there's no other way to change it. I've opened it back up again. I've opened up the corresponding practice test 2 again, so you can, if you've got to open online test that you haven't taken, I've given you the practice test to prepare for it, and you have till Sunday to knock it out. And you might have more than one. There was a couple students that had more than one, so make sure you do that. The other thing is, I would like you guys to make sure you go ahead and read at least half of chapter 10 before next time, and pay attention to your emails because I might email you today or tomorrow or the next day, no later than Friday. I might email you and ask you to watch certain videos to get us ahead in chapter 10. So you're free to go. If you haven't already chatted me your first and last name, make sure you do. And thanks for helping, Will, by the way. I saw you were typing in the row and the sigma and all that good stuff. Thanks for that. I'm glad to having somebody be interactive, and please keep it up. I'll wait here until the last person leaves in case anybody has any questions.
Thank you. Have a great night.
You too. Thanks, Michelle. I think that was Michelle. Yeah, it was.
Hi.
Hey, what's
Hello.
going on, Chris?
I have just a general physics question.
Yes.
Okay, so like the Artemis 2 just launched
Yeah.
and they just got to space and they broke atmosphere. So like when you're leaving Earth
Uh-huh.
and when you leave the atmosphere, do you lose some of the 9.8 like the drag, the gravity constant, or do you lose all of it until you're
No,
way out in space?
that's actually a really good question. In fact, the way you can answer it to make sure you're right is you realize that the moon is farther away from us than any of our international space stations or most of our satellites and all that. Actually, all of our satellites, they're all closer than the moon. And you know the moon stays there because it's got gravity pulling on it. If it didn't, it would just go off in a straight line and leave our Earth. So
Mhm.
gravity does exist outside of the Earth and outside the atmosphere, but it does get sequentially smaller depending on how far away you are. The reason why the astronauts feel the weightlessness is that they're actually in free fall. So it's sort of like if you've ever ridden Apollo's chariot or rode
Mhm.
over a railroad track in your car at a good speed, you
Mhm.
feel that sort of butterflies in your stomach. That's because you're in free fall. And when you're in free fall, you're actually experiencing weightlessness. So that little feeling you get on the Apollo's chariot or the shorter duration that you get on crossing a railroad hump, that is the feeling of weightlessness. So does that help?
Yeah, it's like as the it's is it one of those equations where it's like as a limit approaches a certain value and that's why it's trailing?
Yeah, that's another way of looking at it. And we did that, for instance, when we covered conservation of energy. We talked about the potential energy associated with the Newton's gravitational force, and that gave us that U equals negative GMM over R. That
Mhm.
was found by taking the limit as R approached infinity and setting U equal to zero there. So yeah, it's sort of the same thing. The farther you get away, the lesser the gravity pulls on you.
Okay. All right. Thank you very much.
No problem. Good question. Ask me anytime. I like that stuff, and it's good that you're paying attention to science that's going on outside the classroom. That's helpful as well.
All right. Thank you. Have a good night.
You too. See you, Christopher. How about you, Riley? You have any questions, sir?
Can you hear me?
Ooh, I'm barely hearing you though. Let me see if I can turn it up. There you go.
Probably my headphones.
I got you. Yeah, I hear you now.
So I was able to schedule the face-to-face test for Friday at noon.
Okay, that's no problem.
Um,
I will make sure that they are okay with that. They'll probably ask me, and when I see that, I'll reply. But if I remember, I'll send them an email beforehand.
okay. I had some quick questions about grades and availability of the practice test.
No problem.
Um, I'll combine two of them real quick. In the grades tab,
Hmm.
I'm seeing a practice test three for chapter 1 through 5. But that's not a practice test that is on any of the modules or underneath any of the.
Yeah, so there's a lot of different ways students can get to their different places in their Canvas page, and I don't know all of them. Because of that, I've got assignments that I've made in the past that automatically appear. If they're not in one of the modules that I require you to go to, which include the weekly modules, the practice tests, the online tests, and the face-to-face tests, then you don't have to do them. So I'm looking in the practice or in the was it the practice test that you said you saw an extra one, or was it the online test?
Yes, practice test three, or
Yeah.
yeah.
Gotcha. Okay. Yeah. So if you'll notice, if you look in my practice test modules, I got practice test one, practice test two, practice test FTF, TO1, TO3. That's a different one than what you had. That the one you said went through five. So that 1 through 5 was like an old semester. Probably wasn't even last semester. It's sometime after that or before that. Then I've got PTO4 and then PTO5. All of those are actually ones you have to do. Nothing else do you have to do.
Okay. And
And I,
so that'll be the same thing for I was just wondering because the face-to-face test for Jada popped up as an individual grade too.
yeah, that was a student had a little bit of a problem and stopped in the middle, so I had to make them a new test. So I made sure I put their name on it so you wouldn't think that that was something you had to do. But it is a contradiction to what I just said. So thanks for pointing that out. That's a good for me to have this on a video to let everybody know. Hey, I made that for Jada. That means it's only Jada that has to take it. But good question. I appreciate that. By the way, I think you were the one that asked me about labs. I've gotten 3 more labs graded, so I should put those up either tomorrow or Friday, but you're going to have a lot more labs, so that should help you. Oh, now I just remembered. The other thing that I wanted to let everybody know is I normally have my lab tomorrow at 10 a.m. I'm at a doctor's appointment and I might not be able to get back in time, so I might not be able to do it till 11. So I'm planning on doing it at 11 instead of 10. So if anybody's trying to come, hopefully they'll see this message and understand that.
Okay. Um, for the face-to-face test
hmm
too, um, is there any way I could have some of the practice tests unlocked? Or
Yeah,
I see
you
there's
should.
not.
You should have been. I thought I already did that for you. Very, very good. I'm glad you asked that too. I'm gonna open it for you right now because yeah, you get to do that up until the day you take the test.
And would you recommend with the practice test you have the separated chapter 5 and 6, chapter 7 and 8. Do you recommend just going through both of those a lot and then also the 1 through 4 since it's a cumulative thing? I can never
Yeah,
pronounce
really,
that.
all you have to do is just work the practice test. But if you discover that you're having a problem with a particular chapter, then go and do those chapter ones. Otherwise, the practice test it literally has the same questions as the chapter ones as well. It's just doing them, with all the chapters so you don't see them as often.
Oh, is there a specific one for 1 through 8 or just 5 through 8 or is it those two?
It's just that there's one for chapter 5, one for 6, one for 7, one for 8, and then there's a practice test for 1 through 8, and that's what I'm doing right now.
Oh
It's
yeah.
called PTO5 OT04 and F2F TO2 chapter 7 and 8. It says it's 7 and 8, but it's actually 1 through 8.
Oh, okay, okay.
Yeah, all of
Sorry.
them are. Let me show you something, for instance. So I'm going to stop sharing right here. And now I'm going to start sharing this one. So what you're looking at right here is PT05, which is the practice test that I just suggested you do. If you look at
Mhm.
these questions, you'll see this is from bank 1 to 8. 7, 8, 1 to 8, 7, 8. So that's the way I make these tests is they have in this case I pull out one question from this bank of 42. I pull out one question from this bank of 37, but then I choose 2 questions from this bank of 310. So yeah, it covers all of that.
That is a large bank. Okay.
Yeah, that's why some students are coming to me like I'm still seeing new problems. I'm like, yeah, there's a lot of questions there, but if you've been doing this the whole time, then those numbers are a lot smaller because you got to see them chapters 1 and 2 when you were doing the chapter 1 and 2 practice test, and you got a large fraction of them out because the fraction was a lot smaller then, or the number was a lot smaller then.
Yeah. I was actually confused about that a little bit because with the face-to-face test of 1 to 4, if I recall correctly, I think you had said that 100% of the questions came from the practice test, like the banks and all of that.
Yeah, but you might
And
not have seen one of them.
I took that, and I kid you not, I think I saw 5 of the 17 questions before.
Oh, geez,
It was,
that's a really small number. I'm surprised that it was that few. Now, that being said, a lot of them, well, yeah, that could be, yeah. They all came from the bank. It's just a matter of when I rendered them non-multiple choice, they looked a lot different. So it could have been that you were seeing ones that were familiar, but they didn't look as familiar because they were no longer multiple choice, and the numbers changed. But yeah, I wouldn't be surprised to find that you, in rare cases, only had 5 of the 17 you'd seen before. But I do have students that take it. In some cases, they'll do 40 individual practice tests. I think they're just memorizing them. That's why I had to start making these tests where they weren't multiple choice.
yeah, I took the practice test for 1 to 4 13 times.
There you go. Yeah, that's plenty. If you're approaching 8 to 10, you've got enough. And really, that's if you're doing it right, meaning you're learning how to solve the problems when you're doing them.
Mhm.
Working 8 of them is probably plenty because that's a ton of problems to work. If you're working them to try to find out the right answers and to hopefully see all the questions you've seen before, then you're probably going to have to spend a lot more time doing it, and it's just not worth it, to be honest with you.
Oh yeah, no, I found it was a lot better to just use them as more of a formula, like
Hmm.
familiarization, just learning how to work the formulas in different ways, trying to find different variables and all of that.
That's it. It's a whole learning process. That's all. And it's, however you figure out that it makes sense to you, the better off you'll be. It's way better to get a problem partially correct, but understand how it's done than to get it completely correct, but not understand how it's done. Because ultimately, if you're wanting to be an engineer, you've got to be able to apply this stuff later. And if you're not understanding it well enough, it's not going to work out. So it sounds like you're doing everything right.
Sweet. All right. Well, I appreciate your time tonight.
No problem. You have a good one,
End up
Riley, and let me know if I can do anything for you. If you need any help with that, getting that test done, or if you need have any other questions or anything, let me know.
awesome. Thank you, Professor.
All right. Good luck on your test, bud.
Thank you. Have a good night.
You too. Bye bye. See you, everyone. Bye bye.